6 o'clock, Dan, I shall leave that problem to you and introduce Felix, although Felix has already been earning his keep for the past 15 minutes. Tonight, we welcome Professor Felix Schmid. Felix was Professor of Railway Systems Engineering at the University of Birmingham and is still a Professor Emeritus at the university. It would be no exaggeration, although it might embarrass Felix, it would be no exaggeration to say that everyone in the rail industry knows Felix.
Do I need to go and grab them, or we got enough?
Oh,
Please mute yourselves.
Themselves. Let's just do that.
Thanks, Dan.
And can I just ask Dan to allow me to share screen?
Okay, when I've finished introducing you.
Yep, that's fine.
Okay, so my experience is that because he was chair of the railway division of the Institution of Mechanical Engineers, and because he's supervised so many students on the Railway Systems MSc programme at Birmingham and so many doctoral students, everyone in the rail industry knows Felix. You just mentioned Felix, they know exactly who you mean. Felix is graduated from the Swiss Federal Institute of Technology in Zurich in Switzerland in electrical and electronic engineering. And after working there for a short while, he's worked at the universities of UMIST, Salford, Brunel, Sheffield, and finally Birmingham. And during the course of his career, he's become an outstanding expert on rail, especially, as we've already gathered, electrical matters. So who better to discuss tonight an illustrated history of high-speed rail with some other observations on technology than Felix. Felix, the floor is yours.
Thank you very much. Let's hope I can get the share.
Yes, let's hope I can get you to do that.
Yes, I can do that now.
Ah, okay, fine.
Should be okay. I just need to go full screen on my computer, and then I can share probably. All right. Where are we? I think you should have my screen now.
Yep.
Sharing. Okay. Well, good evening, everybody. Originally, this was supposed to be in London, but the room which we were going to use is not available tonight. So it is now sent from Chaltenham-Hardy, which has got a tramway, but no railway. So I just do a very quick introduction to myself. So this is at an event where high visibility equipment was absolutely essential. So you see I'm wearing a high visibility bow tie. And as mentioned, I was the chair of the railway division of the IMechE, and I'm still active at the University of Birmingham, and I do a little bit of consultancy to keep my brain going. I'm very interested in systems thinking, in railway traction systems and railway control, which is really lights on sticks, ergonomics and people in systems. And I'm going to talk about a lot of things which led up to the development of really high speed. And hopefully you will realize at the end that railways must be fit for purpose. Having a high-speed railway is not essential if what you need is something to get
those tablets we got to come home with are nearly 18 quid.
Can you please mute yourself rather than having dinner, because I'm getting very hungry. Thank you.
Yes.
Right, okay. I also need to mention that the railway research at the University of Birmingham has reached a milestone. It was 50 years old last week, and I hope it gets another 50 years, and it's got the new building as well. So if you're ever interested in meeting at the university, that should be possible. So first of all, I wanted to give a definition, say what is a very high-speed train, because that's to some extent what we are talking about. And I'm calling it 252 kilometers per hour, which is basically 70 meters per second. I think 70 meters per second is quite a good way of thinking about it, because it's a very long distance in a very short time, and you get a sort of feel for what 252 kilometers per hour is. And I'm going to talk a little bit about what the railway does, the history of railways and speed, and a bit about the glory days of the Okay. Yes, I've unmuted myself, so you should hear me now. So a bit about the glory days of the speeding trains, times changing and the fortunes of the railway, and then how the railway started to speed up again. A little bit on very high speeds worldwide and how demographics influence the need for the use of high-speed rail. What I've tried to show on the slide on the right is going from 1955, which is the sort of point where railways start to speed up again, 180 kilometers per hour in service, which is the bottom line, was a very, very high speed. And people were running at 330 or so just to demonstrate that you could do it. So the red line is really just about testing. A brief word on the 575 kilometers per hour and how really impressive that is, but that we really don't want to do it in practice. So, come on. Well, I'm starting quite early. In 1820, George Stephenson built 5 locomotives at his factory, at the locomotive works. And Hetton, Dart, Tally-Ho and Star, they were fantastically fast locomotives. They operated on straight track at 4 to 5 miles per hour. Now you might say, well, that's not fast, but that was continuous operation backwards and forwards. Horses could do that for a short stretch, but certainly not on the roads of the time. So really, you can describe that as high speed for the year of 1820. What's even more remarkable is that the locomotive was in use for just over 90 years. I think most parts have probably been exchanged by that stage, but this is a picture from about the 1890s. A very impressive achievement. So going backwards and forwards 8 miles at 4 to 5 miles per hour was pretty good. Now, what do railways do? Here I've got London, and I've got the blue dot around London, and that shows how far you can get by walking at 5 kilometers per hour, which is reasonably fast for walking. And if we go a bit faster, if we go at 50 kilometers per hour, then it gets us well into Kent. It gets us quite a long way into the south of England and a reasonable distance into Hertfordshire, perhaps. If we go at 100 kilometers per hour, and that happened sort of in the 1850s, then we get quite a lot further. At 200 kilometers per hour, we get to Birmingham, and at the other end, into the middle of the Channel. And if we go even faster, then we can make it to Manchester and Liverpool in an hour, which is pretty impressive. So what railways do is that they shrink time and space. And I think that's their main achievement. And that, of course, leads to a lot of benefits. Now, this is a picture of China, a map of China about 2 years ago, and what is in China available in terms of railways. So there's lines which are capable of speeds of 300 kilometers and above. And you can very clearly see that they sort of form a pattern north-south and east-west. And basically the idea is that any point apart from Tibet is reachable from Beijing in about 8 hours by train. So this is the sort of curves which you can see here. So the main populated parts of China, it's about 8 hours from Beijing. And the objective is clearly to create a unified nation at the price of individual freedom, of course, to some extent. But essentially the railway ties together China. And the investment has been huge, and I don't think it's been actually as financially attractive as people might think, because the railway is designed for maximum capacity around the Chinese New Year, and the rest of the time the trains are not that full. So from about 1820, so that's the Hetton Colliery time, railways did sort of shrink time and space for everybody because they were cheap to use. And you could transport food very quickly, easily and cheaply. And people in cities could actually eat fresh food, which before that they couldn't. Poorer people always had to buy rotten food. Now that reminds me of today, perhaps, but I didn't say that. And then you've got milk and farm produce tended to perish en route to the cities. So again, only well-off people could buy it. And more interestingly, or maybe more interestingly, leisure travel became possible for most people because you could actually go a fair way without having to, without losing too much working time, because of course, people in those days were time poor and money poor. So if you could get to Fontainebleau in an afternoon, that was fantastic. And the rich people, of course, could go to the big resorts in France, in Britain, and because it was just a night, and it was a complete change. And also the labor markets, of course, changed hugely because richer people could commute to have a better work-life balance, and skilled and unskilled labor could be moved around easily. And of course, troops could do that as well. They could be moved, which is why the Austrian Empire built up a very, very large network of strategic railways to move the troops quickly to where they were needed. And effectively, the railways wiped out the road and water as competitors pretty much until the early 20th century. So really from 1820 to 1950, I call it 120 glorious rail years, but it's actually 130, speeding across Europe and the world. I don't know how I got that math wrong. And I think somebody has had a very, very big role in this was George Stephenson. This is a contemporaneous picture of the railway through Chat Moss, which was apparently impossible, but Stephenson did it in a very, very clever way. And that railway was built for 30 miles per hour, sort of 50 kilometers per hour, and it's now running at 110 miles per hour, so nearly 200 kilometers per hour. And that's on the same infrastructure that he built. Now, he did a lot of things which were very clever and which we're still doing today. For example, the gradient between Manchester and Edge Hill, which is at the top of the hill going down into Lime Street, the gradient is 1 in 500 at the ruling gradient, which is of course virtually nothing. Even a very weak steam locomotive of the time could cope with that. But we are now still designing railways in order to make best use of the available traction power. And Stephenson, of course, built the successful locomotive for the Rainhill trials, which I've shown here, with the not so good locomotives being shown pretty much at the back here, including the fake one is not shown somewhere. So it was a big success, and a lot of people think that it was speed, that it was the being able to run at 50 kilometers per hour, 30 miles per hour, but it was really about reliability, because you needed to be able to run backwards and forwards between Liverpool and Manchester without breaking down. And Stephenson was very, very aware of that. And when we see his rocket, we also have to think this was the number 19, so he had a lot of experience by that stage. On the third day, rocket covered 70 miles, which means it could travel between Birmingham and Manchester and Liverpool and back, and had a little bit of extra left. Of course, it's still around in the Science Museum. Most of the bits are still around. some bits went missing in between. And then we make a big jump to 1903, and what we can see here is the realization that if you wanted to run trains at high speed for a long time, you needed an unlimited power supply. And an unlimited power supply you can only get by connecting yourself to an overhead line. Now, this was on a military railway, which is why there is quite a few uniforms around, not just railway uniforms, just outside Berlin, and it was three-phase traction. Now, three-phase is actually the best way of doing it, but you can see it created some very significant difficulties. So Siemens Halske and AEG both produced rail cars for this experiment, and they were both successful within a space of effectively 2 weeks. They both demonstrated what was possible with electrical power and an unlimited supply. No steam locomotives required anymore, no coal. Well, the coal was, of course, burnt in the power station. Very impressive achievement to my mind. Now, in the UK, we were still using steam because we had large quantities of coal, and the investment in electrification came much, much later than elsewhere, because it would have been investment which would not have had a direct, immediate return. So this is the Great Western locomotive city of Truro, and you will see that I've put several speeds at the top, because some people, or people who first did some tests on it, said it went at over 100 miles per hour, but actually that was not very true. Sorry, something's gone wrong here. No. So it was probably somewhere between 97 and 100 miles per hour in 1904. So a bit less than a year after the Germans were demonstrating very significantly more advanced technology and speeds. Now, one of the things which is interesting about these steam locomotives is the diameter of the driving wheels. So here it's 6 foot 8.5 inches, which is very large. I mean, there's very few people as tall as that. And
Let's get it to plug in, otherwise it too will fail.
Sorry. So they had to be so big in order to prevent the pistons traveling at supersonic speed, and that was one of the big technology limitations of steam traction. Now this is looking less good. This is about 30 years later. The locomotive did its speed trial in 1935. It was built not very long before that. I'm just having a look when it was, because it was actually built in early 1935 in March, and it achieved this speed in May. Now that's amazing, because it does mean that the locomotive pretty much worked out of the factory, out of the box. And of course, it was streamlined in order to reduce aerodynamic resistance. Now, the Germans didn't sleep. The Germans built their own high-speed locomotive. And now that had even bigger driving wheels, 2.3 meters, 3 of them. It was outshopped in 1935 in autumn, and it ran at 124.5 miles per hour on the 11th of May 1936. Now, why did the Germans build high-speed steam locomotives if they had the technology for high-speed electric ones? Well, as you saw, the three-phase power supply was pretty impossible to build onto a network-size railway, because basically too expensive and very difficult to create points and so on and crossings with those huge current collectors on top of the train. Also, Germany also had a very good supply of good coal, so they did manage to continue using steam well into the Second World War and still built a few steam locomotives after the Second World War, just as Britain did, while many other countries had given up by that stage. Now, of course, we have to mention Mallard. Mallard was another one of these miracle locomotives, not in terms of its speed performance, but in terms of the time it took from getting onto the rails and actually doing the speed record at 202.58 kilometers per hour. Now, unlike all the other earlier UK trials, this was actually measured with a dynamometer car, so we can be sure that it was achieved. It was on a slight falling gradient, but I think that shouldn't take anything away from the achievement of running a steam train at 200 kilometer plus in 1938. Of course, there was an element of competition with the Germans and with the French, even at that stage. Now, until about the late 1950s, even after the Second World War, the railways had it quite easy because post-World War II, all the economies geared up to replace damaged assets. Railways were needed for the freight moves. Many railways assets were rebuilt like for like, even where it wasn't necessary because there was no traffic. And there were ever-growing quantities of people and goods. And at that point, people started to run trains at 140, 160 kilometers per hour. And if you ran a train at 200, all the newspapers would talk about it. And in many countries, railways were still a source of national pride. However, cars started to achieve 70 miles per hour. And the only reason why they didn't take over from the railways was where the roads were slow and the cars were unreliable. And that changed with the introduction of lead in the fuel, which of course we don't like very much. The middle classes became wealthier. They had more aspirations. The cars became much more reliable. The motorways came in on the German example. And by 1970s, there were lots of motorway networks around the world. People wanted convenience and flexibility. They didn't want to be tied to a train timetable. Passenger and freight traffic avoided the railways more and more because, well, it's so easy to get a lorry to your factory, which then takes the goods directly to your customers. And airplanes, although they were still quite expensive, they could reach a lot of spaces in 2 hours, where normally you just couldn't do that. And I think an important element is, and I don't know how many of you feel like this, when you're driving, you're in control. When you're on a train, you're not. It's the train which is in control and which, or rather the driver and the timetable, which allows you to do things. So at that point, the railways definitely had to act. And they did, and particularly the French. German state railways had conducted some trials with high voltage at industrial frequencies, so that's 20 kV at 50 hertz on the Höllentalbahn, which is a steeply graded railway. And they did that in 1937, but then the war happened and they didn't do any more. And the French suddenly saw this and they said, we are reaching the limit of the power levels of our steam locomotives. We can't go faster and we can't pull heavier trains. And it's extremely expensive. So having a lower cost form of providing infinite power levels was a good idea. And so they adopted this technology. They increased the voltage from 20 kV to 25, but pretty much copied the Germans. And that allowed trials at very high speeds. It allowed fast electric trains in France and Germany. And in about 1964, and we're going to come back to that, the Japanese opened their first high-speed line, first Shinkansen line, which was probably a huge step forward. And then I'm going to talk a little bit about some other silly things. But this is basically the trial at 330 kilometers per hour. Now, that's not a high voltage railway. It's a 1500 volt railway down towards the southwest of France. And what you can see at the back of the train is a cloud of dust. Now, where did that cloud of dust come from? Well, you can see here, this was the track after the tests. Basically, the forces of the train demolished the ballast, moved the rails. So this was a two-off trial. And after that, they had to actually refettle the railway completely. I think they actually had to rebuild it. Now, there was lots of other developments at the same time. They wanted to go faster, so the French actually built a gas turbine powered train, just as the UK did for the experimental APT. And then came the oil crisis, and they realized that the French had to move to electric traction because it was just not affordable to do anything else, because France didn't have a source of oil. They built the ligne à grande vitesse between Paris and the Lyon suburbs, and I'm again going to talk about that a little bit later. Britain built the diesel high-speed train because we had fuel from the North Sea, and therefore it seemed to be no problem. Germany moved to 250 kilometers per hour electric and actually briefly held the speed record. France then captured the speed record. So a lot of things happened in the 1970s, 1980s with speeds going up. And of course, France demonstrated its superiority over the rest of the world with a record train run in 2007. So this is the 1990s test at 515 kilometers per hour. And you can again see the dust from the ballast, which is being crushed to the end. And then here is the absolutely amazing train run at 574.8 kilometers per hour. And when you translate that into meters per second, it actually makes sense, because 160 meters per second is very, very impressive. Can you see cloud of dust here? No, it's because the train has been improved hugely and the infrastructure has been improved a great deal. So there's no vibration going through into the ballast, killing it. There's also been some good experiments with diesel traction. So on the left-hand side is the HST, which was doing a record run in 1987 at 240 kilometers per hour roughly, but the Spaniards got it faster at 260, pretty much 260 kilometers per hour in 2002. But really, diesel traction is not a solution, because it simply doesn't have the staying power over longer distances. And of course, the pollution is also a big issue. So it's just a sort of picture of how this speed development happened from rocket steam locomotives as far as Mallard. Mallard really was the peak of that technology. Then the electric traction, and in between also the green bit is the diesel traction with the Talgo train in 2002. And then, of course, electric traction is the winner, the red line going up there into stratospheric realm. Now, you can see that I've got something which is called very high speed rail, up to 360 kilometers per hour. And people do that. The energy cost is very high. The technology has to be very advanced, and maintenance has to be absolutely amazing. SSR is actually silly speed rail, because why would you try and do that? Because, well, the only reason why you might do it is to reduce the journey times of journeys of 5,000 kilometers. But really, is that necessary? I think it is definitely silly. So There was alongside this also some 100 years of expensive and not always useful experimentation around the world, and that's sort of interlude in the rest of the story. So why am I showing this? This is definitely not high speed. This is the Wuppertaler Schwebebahn, but it's important because it actually doesn't take any road space. It doesn't take any valuable ground. Traffic can still move underneath. And that's actually quite an old system. This is the so-called Emperor's car from 1902. So having a monorail system with electric traction gave you a very, very good approach to using scarce space. Now, somebody saw that in Britain, Mr. George Benny, and he created his own railplane system of transport. And you can see there's quite a lot of that reminiscent of the Wuppertaler Schwebebahn. It's also got bogies which are running on a single monorail up in the air, and then it's got rails at the bottom with wheels which prevent the train from swaying. And his idea was that you could use the Benny railplane system over the existing railway, which could carry goods and commuter services, suburban trains, whereas the intercity trains would fly over the top. Now, we might think that was completely mad, but it was actually an extremely well thought out technology. The wheels which you can see up here, double flanged, and they were designed in such a way that they couldn't derail because the support would come into contact with the running rail before it could derail. It had rubber guide wheels underneath to reduce the sort of noise and so on. And the idea was that it would go at up to 120 miles per hour. In his wildest dreams, he actually expected 200. That's why I'm showing it as an example. Well, it was not really very successful. Benny spent about £10 million on it, his own money. And well, you can see it was in the 1930s. So the Great Recession, the worldwide recession, and the sort of first inklings of a world war prevented people from spending money on this. But basically, it was very lightweight, 5 tons, just over 5 tons without passengers, which is incredibly light. It was diesel powered, but he had already decided that any real implementation would be electric. And he had a very clever brake system and also in-cab signaling, which is today what every high-speed railway needs, because the driver simply can't pay attention to something which is line side. So it was a visionary man and a visionary system. Unfortunately, it was not successful, and the plane was scrapped in 1957, just before Benny's death. So maybe it broke his heart, you never know. Now the Germans, a little bit later, built this fantastic rail plane of their own. Franz Kruckenberg built the rail Zeppelin, Schienen Zeppelin, 2-axle vehicle with a diesel engine, and well, it was actually it was an aeronautical engine. It wasn't a diesel, and a propeller at the back. So you can see it looks quite impressive, and the contrast between the 1930 steam locomotive and the Kruckenberg lightweight aluminium machine was just amazing. Now, the propeller was not vertical because it needed to press the train down onto the track. It was also not a success, and I think there's definitely no chance of people standing in front of the yellow line in this particular case. Maybe we should introduce that in the UK. So I think that shouldn't have come back here. Oh, Oh, yes, okay. Now, having a power system which did not need the wheels on rail led Jean Bertin to invent the Aerotrain. And the Aerotrain was an interesting concept. It was a air suspension, it was with an air cushion underneath the train, so no friction effectively. And he chose jet engines in order to power his train. There were, I think, 3 prototypes, and this is the 4th prototype. It seated 80 people, so it was pretty much like an aircraft of that era. The engine was a Caravelle engine. Now, Caravelle was banned from most European airports because of the noise which the jet engines produced. So it was not perhaps the best idea to use that on a train. But it reached a world speed record for a land vehicle on the 5th of March 1974. They built a fairly decent sized test track, but the system died largely because of the noise and largely because of the energy consumption. However, the Americans saw this and they thought this could actually lend itself to the links between American cities, which are rather further apart than European ones. So 3 companies produced prototype trains funded by the government. And the one we see here actually used steel wheel on steel rails. So it didn't use magnetic levitation or an air cushion, but it used a linear induction machine on the right-hand side, as you can see. These pictures are courtesy of the Transport Museum in Pueblo, and the one on the left shows the Garrett train before it was restored in an aeronautical museum. Now, when I saw this, I was very puzzled because you can see that there is a air intake above the cab, or rather above the train, and in the picture on the left there are also 2 jet engines. Now, why the hell did they do that? Well, they very quickly realized that for a prototype you couldn't spend money on an electricity supply system next to the track. So, and they thought that at the speed of over 250 miles per hour, none of the existing systems would actually work. So the air intake is for an internal jet engine, which was used to produce electricity, which then was used with the linear induction motor. Now the unit has actually gone into the museum. The 2 extra jet engines were needed because the track was too short. So the top is the restored Garrett train without the additional jet engines. It actually looks quite nice. It was tiny, of course, as you can tell from the persons working on the undercarriage. The Rohr Industries have bought the French license for the air cushion train, and they built a train, which we can see on the bottom right hand. It's a much better design than the French train. It had linear motors rather than jet engines. It had a current pickup system, which we can see down here. So this is the pickup, and so it was running on an electrified railway. These are just air intakes here for the cooling of the systems. Unfortunately, they finished their train very, very late, and it only did a couple of test runs before the money ran out. But it was a very, very elegant design, again, very lightweight, and they managed to make it extremely quiet. Now, what you see here is the third rail arrangement, and it's actually 3 rails. So this is basically going back to the wonderful system of the German with a 3-phase supply. which is the best form of electricity supply you can imagine, because it delivers very constant power. And they had a working system, but I think it would not have worked at 200 kilometers per hour. It was a very good design, though. Now, the last sort of, or not, the second to last example of mad systems to some extent is the Emsland test track of the Transrapid system built by Siemens. It was a very successful design. It was a very good construction, high efficiency, and you might wonder why you can be high efficiency at over 450 kilometers per hour. Well, it was because the vehicle was again very light, it was very low, and the infrastructure was the motor. The train was just like a projectile. The problem with the infrastructure, of course, was that to build a set of points for this was very difficult. And you can see this flexible piece of guideway, which had to move sideways. It took about a minute. It wasn't long, but I was always a bit worried. It was a very nice journey, very comfortable, but unfortunately, their technology of the traction power and the train was fantastic, but they actually didn't have a signaling system. So on the 22nd of September, the train, this particular train here, collided with a maintenance vehicle, and it was basically the end of the German high-speed dream. There is an installation like that in Shanghai leading to Pudong Airport, but it's basically just a fancy thing. It's not a useful thing. Now, the Japanese, of course, have gone further. They continue to believe in magnetic levitation, and this is their active magnetic train, which is currently under test, and there is a line being built for it to go between Tokyo and Osaka, and we're going to mention that in the future as well. So now we can go back to ordinary railways and why we actually need high-speed railways. There's market issues, politics issues, and we need to think of how we can achieve it technically. And basically, very high speed is not so easy, and it's not cheap. Now, this is a diagram from the UIC, which shows where high speed can be fastest. High-speed rail is fastest between sort of 150 kilometers of distance and 800. Conventional rail is really only faster in the sub 400 kilometer range, because you're only going at about 200 kilometers per hour. And air traffic really only becomes better at 800 kilometers per hour. And you can see that quite easily here in this very old graphic, which shows the impact of high-speed trains. So on Marseille, Paris to Marseille, in 6 years, basically, the railway took virtually the whole market. Not quite as much as in between Paris and Brussels, where railway is more than half the total traffic and air traffic no longer exists. But basically, road traffic is for people who can't afford the train fare, and largely small groups of people make it cheaper. So it's not really just about high speed. It can also be about for other reasons. It's about transport capacity. If we don't have enough capacity for railroad and air traffic, we get congestion in all modes, which we see in Japan later on. If we have high-speed rail, then it creates capacity for freight and commuters by aggregating services on the conventional railway, and high-speed for the long-distance services. And of course, there's also a growing requirement of populations for mobility, and faster trains can satisfy that particularly at relatively low energy cost. That's, if we look at these, sort of this list is still current. China, most of the reasons for the high speed is capacity and air congestion, because by building high-speed railways, you can get people out of the air into the less energy-intensive and equally fast rail mode. The Shinkansen system was about capacity and competition with both air and road, but largely air. The same for in Paris-Lyon. In Italy, the Direttissima were built for capacity, and then competition. And the latest projects in Texas and California are about capacity because air traffic is reaching the limits which are possible between those cities. And there's a few more. Now, these are not capacity and competition. They're about national integration in China, as I've mentioned before. The Great Belt Link and the Öresund Link in Denmark and between Denmark and Sweden are about interregional integration. In HS1 in the UK is about international integration. And France, all its high-speed lines are about national or international integration. Spanish, very much national. We'll see that a little bit later. Great British, HS2, national integration and capacity. It's an expensive business. And then the Great Britain Northern Powerhouse Rail, which is currently suffering somewhat, again, for integration and capacity. Now, I've got sort of a rule of thumb. If you've got 300 kilometers between major conurbations, then it's worth thinking about high-speed rail. And this is Korea, or rather, well, you can probably see that it's South Korea, because if you want to see North Korea, it's here. And that little dot is Pyongyang by night. And there's a port here. Everything else is just empty, or rather populated by a rather poorer society than southern. And so if we look at Seoul here, which is, of course, the capital city, and then we have a corridor down here of high population. When I went to Seoul some 20 odd years ago, there were 28 747 trains per hour in the morning peak between Seoul and Busan. Now that tells you something, and that tells you basically a high-speed railway is viable. So Seoul is here, and you can see the distances. All the major cities are outside this 300 kilometer radius, and that's where the high-speed rails are going now, of course. So distances on the left, and this map is on the left is the same scale as the Korea by night map, and you can see the plan for the network which was done, and the most recent one is from 2021 with a common core here, and then a route down to Guangzhou and here to Busan, and it takes in a lot. And then this is a fast conventional line, and this is a new very high-speed line going into the east of Seoul in order to relieve this very heavily loaded track. So a very clear political dimension and a very clear demographic dimension to building a very high-speed railway. This is China, and I just thought we could come back to that and look at the map of China by night. And you can see very clearly that it's a very big country, and high speed is going to be a very useful tool. So 2,300 kilometers for one of the major connections, and tying Guangzhou into Beijing was a high priority. And our 300 kilometer radius is very, very small. So what this map shows is quite an interesting thing, is the strategic plan for China. And basically you have got east-west axes and north-south axes in order to serve most of the country within this time scale of up to 8 hours, which I've mentioned right at the beginning of this talk. So again, my 300 kilometer radius. Now, France is another interesting situation. So that's another very high-speed rail example where it makes excellent sense. Paris, the 300 kilometer radius around it, hopefully is here, yes. And you can see that most population centers, apart from Lille, are well outside this radius. And so effectively, there is a very significant, almost desert or agricultural area around Paris. So if you want to link things, you need to really go faster, because otherwise people will use the plane. Now, why could France build so much high-speed rail? Well, the main reason was that the land ownership has been widespread since 1789. And in Britain, because we never had a revolution, the land is in a few hands, so it makes it very difficult to build infrastructure. And the government, of course, in France is very keen on infrastructure. And it's also, the land is relatively cheap because it's largely farmland. So what the French did, they had this network from Paris to Lyon, which was a very, very busy part of their network. It was the busiest because Lyon is the second city. And it was an electrified network at 1500 volts, which of course is very, very low powering. So you had short and slow trains, old track, old rolling stock, poor alignments. If you wanted to go down to Avignon, which is down here, down here, that was a night's journey. There were 10 trains per day between Paris and Lyon-Pardieu, and they all took 5.5 hours. So there was a very significant air traffic between the two cities. Now, the French decided to solve that problem by putting in a short, relatively short, high-speed line parallel to the existing one. And that provided a much better service to Lyon and a little bit in between. But the big thing, because of the way the French designed their technology, which was to use conventional railway technology, but very much more straight, with fewer curves and fewer stations on their high-speed line, the trains could leave the high-speed line here and go into Paris on the conventional railway, and they could leave the high-speed line here to go into Lyon. And it allowed trains to leave the high-speed line to go all into this area here, which is called Les Alpes. And if we look at that, there's now 20 trains between Paris and Lyon taking 2 hours. And we've got all these other cities which benefit from it. 2 hours and 50 minutes to Chambéry, which is a favorite tourist resort of the French, and 3 hours and 10 minutes to Grenoble, which basically tied in this whole area into Paris, but it also allowed cities like Lyon and Grenoble to develop their own commercial centers and their own universities to a very great extent. Lille was also tied into this system with the line going to the north, and Marseille and Montpellier came in as the next steps with the line to the Mediterranean. And again, you can see Avignon, instead of a whole night's journey, is now 2 hours and 38 minutes, 9 trains a day. Marseille, 19 trains a day, whereas before there were about 5. So the airlines were wiped out completely in that connection. And then extra bits were built in order to reach Mulhouse, Besançon, Lausanne, etc. at greater speed. So it was a huge development. And this is just a map of the lines which were planned in about 2000. And this is what the network is starting to look like now. So the line which we have just been looking at down to from Paris down to Lyon and Marseille and Montpellier, the connections into the rear country, the line from Paris to Strasbourg and then into Germany, and the line to Rennes, which is nearly in Bretagne, Nantes and Bordeaux. So this is a very much a national project to get people tied into a joint society. And of course, the next stage is the line to Nice down here, so that you can go to your holiday resorts, not with using aeroplanes. This is Britain, again, Britain by night. And you might recognize where I'm sitting, which is here. Jonathan is here as well. I think Julia is probably down here in Bristol. I don't know where Dan is, but there's lots of it's very clear where we are. Now, why have we not been so successful in building high-speed railways? Well, the main reason is that the distances are relatively short. There is London, and here is my cities of Britain, and the circle is here. So a lot of the big cities are within the 300 kilometers per hour from London. If you look at Penzance, that major center of population, that's further away, but it's about 2 months where it needs traffic. And if we go to the space between Manchester and Glasgow and Edinburgh and Leeds, there is only Newcastle as a major center of population. So it's very difficult to build high-speed railways in the UK because the distances are just not so good. The land is owned by very few people, so they have a lot of power, and land is very expensive. And of course, Paris is just outside the 300 kilometers. That makes sense. That's why we have got HS1. So these are just some numbers about the UK, and I'm not going to go through it. But if you look at these numbers, Greater London, 9 million, Greater Birmingham, 2, Glasgow and Edinburgh, 3, Leeds, Manchester, Liverpool, about 2.5, and then the other areas a bit less. So you actually have to look very carefully to be able to build something which makes money, because the population sizes are just not good enough. So sort of the main decision to build a new line is about, is the origin and destination actually useful? Are we compatible with existing networks? Are we removing bottlenecks? Are we dealing with mobility which is already there, or are we creating mobility? Have we got the right traffic forecasts? Is the system safe? And how are we going to reduce the travel time? Is it having shorter distances by straighter railways, better acceleration, or higher speeds? But when we do that, we need to think about where are our stations, how easily can we get to the stations, and how good are the intermodal links. I once came to the station in Spain and discovered that it was no longer in the city centre, but 10 kilometers outside the city centre, and there was an hourly bus. That was not a very successful use of high-speed rail. And of course, if we can have airport links, then we can take people from the airport and take them to a big local distribution network. So I'm going to spend about another 5 minutes on a case study of the Tokyo to Osaka Shinkansen line, and why I think it's a very good example of high-speed rail. It's a good comparison with second generation high-speed rail in Europe, and their approach is a bit different. I hope you can hear the train. So this is not the current generation of Shinkansen train, it's the last generation, but two. But you can see it's an impressively long train running from Yokohama station here to Osaka in a very reasonable time. Now, in the 1950s and the early 1960s, Japan was really growing hugely after the Second World War. Industry grew, service sector grew, and given the nature of Japan, there was no space to build more roads or railway lines. The air corridors were limited, land for airports didn't exist, and noise and pollution became very important issues. Now there's four main islands in Japan, and if you look at the comparison, Honshu is twice the population of Britain, and about 82% of the Japanese population. Kyushu is very much smaller. Shikoku is even smaller. Hokkaido is quite tiny, and even the main city of Sapporo is only 200,000 people. Now, there's a further element of Honshu, and I'm going to show where that is. 25% of the population live in the so-called Kanto plain. And so I think we'll have a look here. So here we've got Tokyo, Greater Tokyo. Down here is Yokohama. Then we go along the coast to Nagoya. Nagoya is here, and then Osaka is in this sort of area here. So you can see the population density in the Kanto plain, which is about here, is absolutely amazing. And the rest of the population is quite significantly on Honshu down here. There's a little bit on Kyushu, and then as we go north on Honshu, there's not a lot to be found. So Tokyo, Osaka, and here we have got the sort of main cities, and of course my infamous 300-kilometer circle. So it's very clear that building something fast between Tokyo and Osaka will have custom from day one. It's about 550 kilometers between Tokyo and Osaka. So a very reasonable distance. If you go at 300 kilometers per hour, you do that in less than 2 hours. And so that's the network which emerged. And the yellow line here is the line from Tokyo through Nagoya to Osaka, the original Shinkansen. And then there's the newer Shinkansen lines through Okayama to Hiroshima, Hakata, and Kagoshima. Now, the line down here in Kyushu is basically just a government extravagance, because it's a very low population, very hilly, and basically the line was built to satisfy the local population. When we go beyond Sendai here, again, we end up in territory with few people. Now, I was talking about the high-speed line. This is the corridor we are talking about. The Kanto plain is 23.7% of the total land area of Japan, so it's quite a lot. But 60% of the population and 64% of the GDP are generated here. So build a high-speed railway, it's going to be full from day one. So Japanese railways used as 1067 millimeter gauge, and that was very successful for a very long time. There was a strong British influence in Japan. Japanese railways were really created by a few Japanese people who had come to Britain. And Japan Railway decided to build not to this gauge, but to standard gauge, because it made sure that no slow train could go on the high-speed line. And that was a very clever move. Also, the standard gauge allowed a greater loading gauge, sort of the envelope of the trains. It allowed greater roll stability, so you could go faster. And from day one, they used electric multiple units, and the line started at 200 kilometers per hour in 1964 for the Olympics. It's been accident-free, and touch wood, may it stay so, for the last, what is it now, nearly 60 years. It's a very successful system, thanks to a very simple approach to life. And of course, the network is now a lot longer, but really the main net part of the network which still makes money is the one between Tokyo and Osaka. So this is the current network. Bits of it still under construction, and it's very successful. Now, this is an aside. The trains between Tokyo and Osaka are quite Spartan. The trains between Hakata and Kagoshima are luxurious beyond belief. Now, one is a private operator and the other one is the government. So it's quite interesting to see the contrast between the two. Again, the distance here. Now, one of the things which I find interesting is the different approach to the infrastructure design, and I hope to be the last bit of my talk. This is effectively the project to build the interchange station at Birmingham, and the strong view in Europe is that high-speed railways require a high-speed infrastructure. In the normal direction, which is what we sometimes call straight, the turnouts must allow operation at line speed. So on HS2, that's 360 kilometers per hour. In the reverse direction, you try to allow them at a speed that is as high as possible, because of course, points are very difficult and very high risk devices and very expensive to build. So the example here of the interchange station near Solihull is you've got station tracks where the trains can get into at 95 kilometers per hour, which is very fast, or at pretty much line speed. Then you've got two tracks through the center, which are line speed and they don't have a platform, and then the same on the other side for the other direction. And about 2 kilometers before the station, you've got these diverging points, which give you at 230 kilometers per hour. So the idea is that you start braking about 6 kilometers before the station, and by the time you get to here, you're slow enough to go through these points, and by the time you get to here, you're slow enough to go through here. And that's the UK approach. And you can see that the technical equipment you need for this is quite significant. So here, 160 meters between coming into the points and then here going out of the point, going onto the straight track again. But if you're using 240 kilometers per hour, then this becomes 440 meters. So that's half a kilometer, basically. That's very, very expensive to build. It's very expensive to maintain in a safe condition. So not ideal. Then I came to Japan and I looked out of my hotel room and I thought, what? This is infrastructure from the 1940s, 1950s. Because if we look here, it's a 50-meter long point. That's a maximum speed of about 60, 70 kilometers per hour. Why have I come to Japan? I can see that in England. And that was a bit sort of, well, I wasn't right, I was stupid. Because the Japanese have a slightly different approach to defining their railway. So in Europe, the first thing we do is we identify the demand, the quantity, the journey time, the competitors. Then we design the rolling stock. Then we design the infrastructure. No, I have to go back to this. So first thing is demand in Europe. Then that's the same in Japan. Then we define the timetable, the number of trains, the service pattern. Then we design the infrastructure, and then we design the cheapest train which can cope with the first three things. Now the Japanese have got a different approach. Yes, they identify the demand, and we've seen that was obviously going to be fantastic. Then they designed the rolling stock with the traction power and how many axles of the train are powered to get the maximum adhesion. And then they designed the infrastructure, and then they defined the timetable. So it's a very strange approach, because it's a given in central Japan, in central Honshu, that you have got the demand. So in Japan, you build points which are able to do 70 kilometers per hour to get into and out of stations. But you have trains which are much better than anything which we have got in Europe. The Shinkansen, the latest series, weighs 705 tons, but that's 12. Let me see how many axles is that? 64 axles divided by 4. Is that 16 carriages and 705 tons? Lots of seats. So each seat has got a very little mass associated with it, and you've got a huge amount of power. So 17.1 megawatts is, well, if you can't look at it in terms of fan heaters, well, a fan heater is 3 kilowatts, so that's about 6,000, 7,000 fan heaters, all powering a train. So therefore, it accelerates fast and it can brake fast. In Britain, we've got the Pendolino, which is a very good train. It weighs 460 tons, but it has 960 kilograms per seat, and the power rating is significantly smaller. And in the distance where a Japanese train reaches 300 kilometers per hour, a Pendolino reaches 200. So these are the important points about it. If we have got lots of powered axles, and in the Shinkansen it's 56 out of 64, on the Pendolino it's 14 out of 36, then that allows you to accelerate and brake very hard. So this is one of these newer trains. So you brake hard, you accelerate fast, hard, and the most important thing is, because you've got very big traction motors, you can brake electrically from 270 kilometers down to 30 kilometers per hour. And I've got to give you this anecdote. When I went to Japan with a guided tour of the UK railways, we went to the research center, and in the entrance there were 3 traction motors, traction machines, electric machines, displayed showing different generations. And I looked at it and said, that must be wrong, because the smallest motor is the newest, is the oldest. No, it's the newest. No, start again. The smallest motor is the oldest, and the biggest motor is the newest. And so in the meeting we had afterwards, I said, are you sure these are labeled correctly? I was being polite in a way. And they said, of course it is, because we're using bigger motors so that we can brake better, and we can use more of the energy, the kinetic energy, and feed it back into the overhead line. So that means that because of the high braking ratio possibility, you can come to these turnouts just before the station, go down in speed, and then go through the points and into the station. And that's what the typical Japanese Shinkansen station looks like on the Shinkansen from Tokyo to Osaka. You've got very short station platforms. You start braking more than a kilometer later, and therefore you need less space, you need less equipment along the line, and less land. So there's a lot of advantages to that. And then I decided to do a sort of comparison. Now, this is going to be quite complicated. So all it tries to show is that the Japanese train in red starts to brake later and brakes harder, and therefore the following train can go through the points in the straight direction very quickly afterwards. So there's very little loss of performance by having trains, by having a cheaper infrastructure. Sorry, where am I? So that's the infrastructure at the station, and it just shows that the Japanese train is virtually at the station by the time it goes through into the platform and then stops. In the Japanese case, you're in the station much, much more quickly. So there's lots of things which the Japanese do differently. They have very simple S&C, no expensive kit, steep gradients and tight, relatively tight curves, and a very simple signaling system. And on the Shinkansen to Osaka, which is just seismic very active, they use conventional ballastic track, and they have a lot of maintenance each night. And this is the last Japanese slide. So what I wanted to show here is the future maglev line, which is being built along the test section as well. And that's supposed to come into operation in about 2030, but there's a hold up with a local authority who doesn't want the line to come through. And down here, it just shows sort of the three service patterns: fast trains, medium speed trains, and slower trains, and how many stops there are. Now, the high-speed line from Tokyo to Osaka is 550 kilometers, and there are 15 intermediate stops. What does that do for you? It makes for very happy local populations, because even small towns got a station, and therefore there was very little resistance to the railway. We do it differently here. Okay, this is the last sort of bit of a summary. I've talked about the high-speed rail principles in Europe and China. You start by building an infrastructure that allows continuous high speed. You have very few dwells. You have very expensive station approaches, and you don't worry about the effort and cost of maintenance. That is just has to be paid. It's the best technology that money and time can buy. Whereas the Japanese have the need for speed, but it's based on an evolution. It's a railway that satisfies a need and is acceptable to the stakeholders. They keep cost and environmental impact as low as possible. Now, this is just the last slide, couple of slides, where we are better than the Japanese. These are two cleaning crews which wait for a train to come into Tokyo main station, and then they will descend on it like a squad of highly trained special forces troops. They clean it within 12 minutes so that the train can be loaded again and goes out again. Now, that is a huge crew. It's about 20 people in each. The men have slightly, or the people in blue have slightly different roles to the people in pink. Now, this is Super Lady. And Super Lady used to work for Virgin, and she now works for Avanti West Coast. And she goes constantly up and down the train collecting rubbish, cleaning tables, looking at the toilets are okay. And that has a phenomenal impact on the staffing of the train. So I've created a Avanti West Coast train, and the Japanese Tessei train is the Japanese contrast. And what you get in terms of cleaners is just amazing. In Japan, they would throw 44 people at this train in Tokyo. In Avanti West Coast would have to throw 11 people at it. And it's basically because of the two onboard cleaners who keep the train in a good shape, which also, of course, makes it easier for people to be well behaved. So that's the end of my talk. And I think it was suggested that there might be questions.
Uh, Felix, that was a wonderful survey. Thank you very much. And not only did it make me very nostalgic for traveling around Japan in the last century, where they certainly did shrink time and space, as you suggested, but it was a real tour de force covering an enormous range of topics and issues. Dare I trespass on people's time by kicking off? You showed the SNCF trains running fast and wrecking the track. Now, clearly, this is something to do with the wheel-rail interface. Evidently, the French didn't understand that at the time, although we've understood it much better since. Why didn't these early trains just leave the track?
Well, the damage largely came from the particular design of the French locomotives. While the dust came after the locomotive, the carriages did far less damage. The locomotives had very heavy axle loads and very high unsprung masses. Unsprung mass means that the wheel, the axle, and the traction motor is pretty much fixed together, and it acts like a sledgehammer on the track at these speeds. And the Japanese trains, the Pendolinos, they have got very well suspended masses. There was a second
and lateral
problem,
suspension.
the vertical suspension.
Yeah.
The lateral suspension is much less important for that. The lateral suspension keeps you on the tracks.
Exactly.
The other problem was, and the French didn't learn from those early problems, was if you use limestone for ballast rather than granite, it doesn't like that sort of action. And the high-speed line between Lyon and Paris had to be reballasted about 15 years after construction because the limestone had simply given up its ghost. Yeah, so that's
okay. Have we got other questions? I'm sure we have in such a huge audience.
Yeah, I've got a technical question, a couple of technical questions.
Right.
We've already got a problem in this country with power supply to trains. They're arguing at the moment on the East Coast line about how many trains they can get along the track because of the power demand. Presumably in Japan, there must be a much more cozy relationship between the railways and the generating companies. And what I'm also thinking about, talk about dynamic braking. When the trains are coming into the station and using electric braking, how much power is going back into the system?
Well, in the UK or in France and Germany, if you brake from 330 kilometers per hour, until you're down to about 150, you're braking largely mechanically with brake discs and brake blocks. When you go down below that, you brake electrically down to about 20 kilometers per hour. And that means at that point you're regenerating reasonable amounts of energy. In Japan, you start full electric braking at 270 kilometers per hour, and then it goes down to about 30 kilometers per hour, which means you recover a much greater percentage of the kinetic energy in the train. And the loss of kinetic energy, the loss of energy through the wheel-rail interface is relatively limited. It's
my question is really how much power is being punched back into the system, and can the generating companies utilize it? If we went over to that sort of system in Britain, which sounds very, very good from the renewable power aspect, could the way that we build the generating system over here in terms of transformer sizes and so forth accept it?
Well, with what's called the auto transformer system, which is much more much more powerful than the older system. The thing is, you don't actually want to feed back to the power stations or to the power grid. You want to feed trains down the line which are accelerating. And so if you have a really well-designed timetable, you will make sure that when one train slows down, another train is accelerating. And therefore, energy stays in the system. And it was it was funny when one of my colleagues and I went to China, and we were asked to praise how they managed to control their metro. They had people who were their task was to make sure that all the trains started at the same time and all the trains stopped at the same time, which meant, of course, that regeneration didn't happen. So we said, actually, you should do it slightly differently. Even if you do it randomly, it will perform better. Yeah. Is that an answer to your question?
Well, not quite, because I mean, when the East Coast main line was set up, it's a single phase AC.
Yeah.
And I understand that when the train, the lines are, it's a different phase from one part of the line to the other. And what the power companies don't like is the other trains whistling along, and then it's suddenly going from one phase to another phase, and that's causing disruption on the system.
That's the classic problem of railways, which is why power companies don't like them. Now, the auto transformer system has longer feed sections, which means there's more likelihood that there are several trains in the same section and that they balance out to some extent. But it is so you when you set up the system, you have to think about timetabling as well as anything else.
And that's a wonderful simulation problem. Vaughan, do you want to come in?
I want to come in.
Oh, John. Okay, John. Yeah,
okay.
Go for it.
It's now 2022. If you were starting now, would you do it in the same way, given the pandemic, the internet, Zoom, and all the things that have happened in the last 15 years?
Well, I'm an optimist to some extent. And what we see is that road traffic is pretty much to the same level as before the pandemic. And that's horrendous. And even if we go to all electric cars, we still produce huge amounts of microparticles from the tires. Well, we produce some on the railway as well, but far less. And if the railway only takes 10% or rather than 8% of the traffic, it will be full. So I think we do need to build more railways and improve the railways which we have got in order to ensure that people use them. And going fast within reason is sensible. I don't think 330 is necessary in the UK, but since we are building something new, we might as well build it to the high standard.
Okay, Vaughan.
Yeah, thanks, Jonathan. Felix, you've explained to me why it was my instruction on getting on a Shinkansen train was to sit down quickly, simply because the accelerations and the braking are sharp, even compared with some of our better underground systems. But one thing puzzles me a bit in your answer to Fred was I recollect that the trains were running at really quite short headways. The line density was very high, and presumably that makes it much easier to balance your electrical power ratings between trains on that line. Whereas if we run on a classic sort of UK headway, that may be more difficult. I seem to remember doing the same sums when we were designing the Channel Tunnel in 74 for 90-second headways. And if you're running at that sort of headway, then the speeds and acceleration, deceleration made it much easier to balance the electrical system. Make sense or not?
That makes absolute sense. And I mean, HS2 is being designed for 16 to 18 trains per hour. I think it's now 17. And so you have got very short headways, not 90 seconds, because you can't have that at 300 and odd kilometers per hour, but sort of 2 minutes, just over 2. And it's auto transformer feed, which means the sections are longer. Now, one of my PhD students did her research on converter feeding. So instead of having single phase out of a 3-phase network, she is using the 3-phase network to create single phase, which is what the Germans do and the Swiss do using electronic devices, because that way your loading of the grid is perfect. It's just ordinary 3-phase loading. And so I think that's something which will in due course happen. At the moment, it's relatively expensive, but as high power electronic devices become more affordable, that's actually a possibility. And those are inherently able to feed back into the 3-phase grid.
Bob, you're another electrician here.
Well, strikes me the trams in Bradford were using exactly the same system in the early 1900s. They're using downhill trams to drag the uphills up. Yeah. But further to that, there's these motors must be under phenomenal strain. And I would think, at what point does the cooling have to become liquid? A liquid cooling system. And also, I've worked on big inverter systems, and the problem is keeping the voltage levels down because they generate huge, and we used to dump huge quantities of the excess regenerated voltage into ballast resistance dumps just to get rid of it.
So a normal electric train has got on each vehicle or on each powered vehicle some rheostatic capability. So if the line voltage goes up and the train notices that, then it starts to dump energy on the train itself. So you don't actually have to do it at the substation or somewhere else. There are already significant numbers of trains using liquid cooling in order to have smaller gear and less noisy. But of course, if you have more, the silicon devices have got higher efficiency, so less need for that.
That question reminds me of Fred's problems with the lift that got us up and down from the Middlesbrough Transporter Bridge on the last Newcomen annual tour, where they had to dump large amounts of excess current. I'm sure Fred still has the scars. Are there more questions, please?
Yeah. What about the cost per mile of track compared to various countries that have installed high-speed trains? I know it varies because of certain conditions, but a typical example.
I haven't got any numbers in my head, but the cost is a relatively small element. I would say below 50% is actually construction cost, certainly in the UK. 50% is friction in the system, which creates delays and cost. I mean, that's just my personal opinion. The Japanese infrastructure is quite cheap. Even the slab track which they're building now is relatively cheap. But basically slab track pays for itself after about 25 years. Before that it doesn't, but which is why it took HS2 something like 8 years to decide to go for slab track. Slab track is where you don't have ballast.
Yeah.
So it's significantly more expensive than ballastic track, but if you have a problem with ballasted track, it's very easy to fix. If you have a problem with slab track, as the Germans found out, it can take months.
And I asked you the question because with all the questions about HS2, whether we should have it and whether we shouldn't, the story's going round that we've got the most expensive high-speed track in the world here. Is that right?
I can't comment because I advise HS2 on systems engineering. I think
Right.
it would not be fair to make a comment on that.
Fair comment. Okay, right.
Very
I didn't
tactful,
realise-
Felix. Mike, you'll have to take Felix out for a drink. That's the way forward.
Okay.
Are there any more questions? Chris, you're unduly quiet.
Oh, you mean me?
Yeah.
Okay. There was something I didn't quite understand in Felix's comparison of the distribution of costs between the Japanese case and the British HS2 case. I thought Felix said that the British case had the best trains, implying the Japanese had a less good train, and yet you're telling us they have all this fantastic regenerative braking on that's much higher performance than the British ones.
No, that was a misunderstanding. The Japanese start once they know that they've got the demand, they design the train to be the best possible train with the highest performance. It doesn't necessarily look as nice inside as it does in a luxury train, but it's the most powerful train you can build.
They look pretty good to me last time I rode them.
But the outside,
that was about 5 generations ago.
Yes, well, I certainly felt that central Japan trains were a bit Spartan.
Interesting. I haven't been on any of the recent ones.
So you build the best train that you can build because the cost of the trains in a normal railway is probably less than 10% of the total cost, if that. That's probably
really?
fine.
Okay, that's very interesting. Thanks. I got no idea it was that low.
Very expensive element.
Hey.
This is Fred, and Bob or Fred will like this. The old saying was the civil engineering on a railway costs 80% or 85% of what it costs to build the railway. Mechanical engineering costs 10%. Electrical and electronic engineering costs 5%, but it has got the ability to mess up the railway to 90%.
I love it. Yes, absolutely.
Good one. Can I bring in Sandro Balestrino, who sent a very rather interesting question about the tube flight systems developed in the 1960s and modern ideas about hyperloops. You haven't mentioned hyperloops.
Hyperloop appeared on one of my slides as the Aerotrain as a failed example similar to Hyperloop. Hyperloop will fail.
We should sell the shares then, right?
The reason why is that, and people seem to neglect this, Elon Musk basically said, here is a concept. He didn't say this is buildable. He didn't say this should be built. He said this is a concept. And it brings together operation in vacuum, which is lower aerodynamic resistance. It's electric. It's very fast. But he didn't tell, and that's the biggest question, there's two questions really which he didn't answer and which I think are not answered, is how would you feed a vehicle every minute into an evacuated tube? Because otherwise you don't get you don't get the capacity, because each vehicle has got, I think, about 100 spaces, if that. If you make the tube big enough to be comfortable, it's not going to work. So if you look at the illustrations of the train, I don't think I can demonstrate it here, but basically you're sitting with your legs high, leaning back in order to use the space. So it's not going to be walking around to the to the toilet or going to the cafe bar. It's sitting there until you reach the end. So that's the first. The first problem is comfort. Second problem is getting these units into the tube and feeding them one in after the other. And the third problem is what happens if there is a leak in the tube. Because the train just next to the leak or just near the leak will stop very, very quickly because, of course, the aerodynamic resistance goes up like that. And the train which is behind it is shielded from that aerodynamic change.
Oh, yeah.
That has also not been answered. There's a picture being shown here by Fred. What are you showing us?
I'm showing you something which I found in the attic yesterday. And it is a paper from 1967 of a vacuum tube system running between Boston and New York. And it has got these cross chambers, which they claim gets over this leak problem and keeps the thing running. I haven't actually read the article, but I've never seen anything quite like this for one of these Hyperloop systems.
I'd be very interested in a copy of the article.
Thanks, Fred.
By all means.
It reminds me of the atmospheric railway in the 1840s.
Right. Without the rats.
Without the rats.
Old idea recycle.
He's not to have Mr. Fontaine's hamster.
Anybody slagging off the atmospheric railway is an enemy of mine.
In that case, Felix, that's your next lecture.
Our badge I'll wear with pride.
Oh, we definitely want to lecture on that, Felix.
Yes.
The atmospheric railway only had to work successfully for about 2 years until the locomotives were strong enough to take the trains up the hills. And it did work for about 1.5 years. So it satisfied the function.
Right, well volunteered to the next lecture. The time is pressing, so I'm going to take one last question, and I'm going to allow Vaughan to come back in his newly elected state. Vaughan, would you like a last question?
Yeah, if I can, Jonathan. Felix, one of the things with Japan has always been speed, because Japan's a funny country. There's next to no flat land. The middle of it's all hilly.
Yeah.
It's like North Wales, but a large country out of it and lots of people. And I got involved very much with high-speed shipping around the coast. That was simply to get the freight off the railway. And part of the reason they've been able to get the high-speed passenger trains in is because the rail freight has been shoved off sea routes, which is kind of interesting, because when I first hit railway work was 1974 with the first go at the Channel Tunnel in real time as opposed to the very early ones. Yeah. And part of that was around, I was an aerodynamicist at the time, or pretending to be, and it was dealing with the aerodynamic drag of trains in tunnels at high speed. I can't remember what the speed was in those days, but it was fast. And part of the reason of shoving trains in thick and fast was that you gained the benefit, and you had all these little cross ducts to shove piston effect round and round in circles. And I looked at it, I wonder where on earth all this heat that was going in the form of power actually ended up, because trains came in at the same height as they went out, and they came in at the same speed as they went out. So there's some energy going in, and where was it going? And it sort of got a bit of sucking of teeth about, oh, it'll all conduct away. Well, of course it didn't. But, you know, when you look at tunnels and high speed, and you look at countries that don't have large open air flat routes, a whole series of different questions start cropping in. Of course, Japan has got the tunnel that goes through to Hokkaido.
Yeah.
Will we ever end up with high-speed trains in long tunnels apart from the Channel Tunnel? Because the Channel Tunnel rail link that I worked on in 1974 started, I think, at Victoria and emerged somewhere near where I'm living in South London before going down existing railway lines.
Waterloo. It started at Waterloo.
And Vaughan, there is a huge cooling set up at Samphire Hoe, just outside Dover, of course, for the tunnel.
I know, and of course, the Samphire Hoe is all built on the stuff they dug out from the tunnel and didn't
That's
have
right.
to move somewhere else.
A good place to put your very energy-intensive air conditioning plant. Felix, what do you think
That's
about tunnels and high-speed trains?
That's where I was going to put it when I designed it.
What do you think of tunnels and high-speed trains? Last answer.
Well, HS2 it has got several. The Chiltern tunnels are not insignificant. They are very long, and their cross-sectional area is huge. Therefore, in order to limit the pressure, effectively the aerodynamic resistance, which is going to be big. The Saikan tunnel between the two, from Honshu to Hokkaido, the speed is limited to 120 to 140 because it was actually built for Cape gauge 1067 millimeters, and then expand. I mean, it had always been intended to go to standard gauge. So, but the trains can't go very fast. They also go very steep down. The tunnel is very, very deep.
Hot.
And so they then go up a mountain basically at the other end.
And it was only built because the ferries sank.
Yeah. Going fast in tunnels is obviously not a very good idea.
Well, that's a good statement on which to end. What was a good idea was to invite you to talk, Felix. It's been a fabulous evening, one piece of genius. And I must say this, I've never seen it done before, was using the maps of South Korea, China, France and Britain by night to illustrate the population centres. I thought that was a remarkable piece of presentation to add to what has been a splendid illustrated talk, worked on many, many levels, and we're delighted to have you here. And we apologise perhaps for firing quite so many technical questions at you, but I'm going to shut down now, otherwise you'll get a whole lot more from this audience.
With this crowd, yeah.
Yeah, so thank you very much indeed. I think Felix deserves a virtual round of applause. Thank you very much.
Thank you.
Bye for now.
It's